Welcome back, Patriots. This is Mr. Love, aka the Math Patriot, bringing you another fun and exciting lesson in the world of high school geometry. We are moving on to our next unit today, the surface area and volume unit. And normally I would be spending a whole lot more time on surface area than I actually am. But I've got good news for you. This year, because we are having to shorten down our units and cut material out, well, I decided that between the two, volume was the more important thing, especially progressing on into your calculus class in a couple years. So we're going to focus a lot on volume. I'm going to talk about what surface area is. I'm going to define all the parts. I'm going to give you the formulas, but we're not going to be doing any calculations with surface area, which is going to simplify things down quite a bit. So here's what we're going to do. Go ahead and talk about all of our different pieces of a three-dimensional shape, and then we're going to decide or talk about what the surface area formulas are, then move on to volume and do all of our examples. Now, before we talk about any of these lateral faces, base edges, any of that stuff, we've got to determine what is the base of a three-dimensional solid. Some people want to say it's the one on bottom or the one that it is sitting on. Both of those, while they can be true, are not the way to think about this at all. You have to think about the fact that a base, just like a triangle, the base can change. For example, on a triangle, I could use this as the base, or on a trapezoid, this here is base 1, that is base 2. It has nothing to do with which one is drawn up, down, left, or right, and everything to do with the concept of what is the base. Now, when you think about a prism, that's why I drew this triangular prism here and this rectangular prism there. Now, what many people will say about this rectangular prism is, of course, the base is the one that it's sitting on. Well, yes, that is true. That definition will not work for the triangular prism above it. We have to revamp and start thinking about the idea about what is a prism. A prism has two parallel faces. I don't care what the base is. It will always have two parallel faces. And in this particular triangle, it is this triangle here, this particular prism, and this triangle here. Notice that will not happen with any of the other faces. If I was to try and talk about the one of these long faces here, let's say this one, there is no base parallel to it. Same thing goes with that one on the back, same thing with the one on the bottom. So a prism will always have two bases that are parallel planes or on parallel planes. And in that case, the only ones that will work for that are this triangular, the two triangular faces. Here's another great hint. It is always named after the base. So when I look at this particular prism here, this is a triangular prism, meaning that the base is a triangle. This guy, the base is a rectangular prism, therefore the base is a rectangle. This guy over here is a hexagonal prism, therefore the base is a hexagon. Another way you can look at this is you'll notice that in all of these, and again, this guy over here is a bad example of it. It's true for him, but it's a bad example. If I was to look at each of the individual sides, you have a triangle. Oops. Let me get my marker here. This front face is a triangle. This back face is a triangle. This side face is a rectangle. The bottom face is a rectangle, and the back face is also a rectangle. Notice there are two triangles and three rectangles. Over here, look at the hexagonal prism. Notice the top one is a hexagon, the bottom one is a hexagon, and then all the ones working their way around the outside, those are all rectangles. So a prism, the two bases are the two non-rectangles. So in this case, the only two that are not rectangles are the top and bottom. Hexagons makes the hexagons the bases. On this one, the only two that are not rectangles are the triangles. Therefore, the triangles are the bases, and it is a triangular prism. Over here, they are all rectangles. Therefore, it's a rectangular prism, and you can pick any face that you want as the base, and it does not matter. Whew. Now, why in the world would I spend so much time talking about which one is the base? Because this idea right here about it is the one that it is sitting on. Please do not do that. Okay? It is done by definition, not by the way that it's sitting. So the reason that's important is because we have got to know the difference between the base and the lateral faces. Now, the lateral faces, as we have defined here, are the faces in a solid figure that are not bases. That's pretty obvious. A lateral edge, I'm going to do this in orange, is any of these that go between the two bases, okay, where two lateral faces touch each other, where two of the rectangles are bordering or where they intersect. Now, the base edge, I'm going to do in green, are any of the edges along the base. Altitude or height are kind of synonymous here. That is, I'm going to do this one in purple. Well, actually, no, I take it back. It's one of these ones in orange. The height is a lateral edge, or can be found on a lateral edge, but it doesn't have to be. It could go down straight through the middle, and it would still be an altitude. Basically, the height perpendicular to the bases. That's the important part. Okay, 6 minutes on the parts of a prism. Now, there are two types of surface area. There is lateral area, and then there is surface area. The difference in the two is, do we count the bases? Okay, the lateral area is the sum of all of the lateral faces, or in this case, all of those rectangles. Now, in here you have a picture of a net. Basically, if I was to take this triangular prism and cut it along the two triangles here, cut it, and then unfold it, we would get this particular set of shapes. Now, notice again, triangle, triangle, rectangle, rectangle, rectangle. All the rectangles are the lateral faces. The triangles are the bases. The lateral area is the sum of the lateral faces, which is essentially just these guys here, this large rectangle. Now, because the lateral area is essentially a big, long rectangle whenever you fold the thing out, or whenever you unfold it, what that means is we're going to be using the area formula for a rectangle in order to come up with the lateral area of all the three sides combined. Now, think about where all the distances of those came from. And I'm going to switch colors here so we can make sure that we make this very clear. This particular side here that I'm doing in orange, all three of those are the exact same length. They are the distance between the two bases, the two triangles, which means that they are here, and they are here, and then here, and here. The reason that there are 3 shown here and 4 shown here is that this particular cut, where I cut it, gets shown twice. Now, let's look at, I'm going to do this in green. This side length here goes exactly right there. Okay, those two. Then in purple, this side length goes there, and in, let's do it in pink, this side length went there. The reason I do that in the 3 colors is, notice what's going on here. If I was to add the green plus the purple plus the pink on the prism, that would be the perimeter of the triangle, or the perimeter of the base. Now, notice what happens on this one. Now, that perimeter of the base, purple plus green plus pink, that perimeter is just going this direction, and that is the length of the triangle. So of the rectangle. So when I multiply length times width, this entire thing is just the perimeter of this shape. So in order to find the lateral area, or the area of those three rectangles, or the one large rectangle, it is just perimeter of the base times the height of the prism, which is where this formula comes in. Lateral area is perimeter of the base times height, and that will be true for every single type of prism you ever come across, even the special ones we're going to talk about here in a few minutes. Okay, there is one special one, has its own special formula. Now we talk about total surface area. I said earlier, this one is just the lateral faces. Total surface area is all faces, which also includes the two bases, the top and the bottom. The only difference is we are adding in the top and bottom base. So our lateral surface area is all the ones on the sides. Then we're just going to add in this base and this base. Now, we're going to use capital P for perimeter of the base. We're going to use capital B for area of the base. I should have mentioned that when we had this one. Capital P is perimeter of the base. Now, the only difference for surface area is we're adding in two bases, and therefore it is the just plus 2b. So you're going to have to pull in any area formula you need in order to make that work. Area of a regular polygon, area of a trapezoid, area of a rhombus, whatever you need, depending on what shape this is. Okay. That's a 1, 2, 3, 4, 5 hexagonal. It's kind of like a Superman symbol, though. A Supermanal prism. Okay, so here's what I want you to notice about a cylinder. Cylinders are actually the exact same things as prisms. If you start thinking about a cylinder as a circular prism, then everything I just said about prisms also applies to cylinders. The only difference is what formula you use for this. So right here, when we're talking about the lateral area, notice it's got 2 pi RH. However, isn't the circumference of a circle just 2 pi r? And the circumference is essentially the perimeter of the circle. So the perimeter of the circle, I know you can't exactly call it a perimeter because it's not an addition of sides, but it's the same concept, distance around the outside. So this is still just perimeter of the base times the height. So it still works the exact same way. By the way, if I was to cut this right here and then also cut it around the top and around the bottom, so make one cut on the sides, what you would end up getting is something that looks like this. Okay, if you don't believe me, try making those cuts on a Coke can and unrolling it, and you'll see that that's exactly what you get. So you still got here a base, and this one is going to be 2 pi r because it was originally wrapped around the circumference, and this is still the height of the circle. Now, total surface area is going to be the exact same thing, except we're adding in the area of the base, and so when we add in the two b's, area of the base, area of the circle is just pi r squared. So we've got 2 pi rh plus 2 pi r squared, or you still get ph plus 2b when you use circumference for this and pi r squared for that. Easy enough. Okay. Volume. All you're going to do for volume is you're going to multiply the area of the base times the height. And that's what this little Rubik's Cube concept was about, was to show you that the area of this one being 3 by 3 is 9. We're going to multiply it by 3 going high is 27. So the volume here is just area of the base times the height. And we'll cover that in quite a few examples. Volume is where we're spending most of our time. It's the easiest one. So there we go. Volume is area of the base times the height. And for this area of the base, use anything necessary to get there. So area formula of a trapezoid, area formula of a kite, whatever it is. All right. Cavalieri's principle. I may have pronounced that wrong. Here's the idea. As long as two solids have the same height and the same cross-sectional area at every level, then they have the same volume. Here's what we mean by this. This prism here on the left. Every single place that I slice it here, slice it here, slice it there, they all have the exact same area B. Now this one is what we call an oblique, because an oblique prism, because it is tilted over. It's like the Leaning Tower of Pisa. It's been pushed that way a little bit. So, however, even though it's tilted over, since it tilts the same on the right as it does on the left, all the way across, the areas are the same here, here, here. You still have that same area B. By the way, it also works on this one. Even though it has a different length and width, it still has the same area. It would be something like this being a 2 by 2, whereas this was a 1 by 4. They still have the same area. And they all have the exact same height. Therefore, they will have the same volume. Now, the reason that's important is mostly because of these obliques. As long as I know my height, my perpendicular height, I can still use the same area or same volume formula as I did before. All right, so let's find the volume of this prism. Volume equals area of the base times the height. Area of the base for a triangle is 1/2 base times height. Now here we've got to start talking about the difference in context. Context is everything. Here, this height is talking about the triangle height. This height is talking about the prism height. So, excuse me, I'm going to highlight this H in yellow. The height of the prism is the distance between the two bases, which is here, this 25. Over here in orange, height of the triangle is this guy, the 12. So we got to keep them correct in context. Is one of these places where we have the same variable, I mean this different things in the same problem. We just got to be careful with it. Let's calculate the area of our triangle first. 1/2 times base of the triangle is 10 centimeters, times height of the triangle is 12. Multiply those through. 1/2 times 10 is 5, times 12 is 60 centimeters squared. Now we're going to plug that in. Capital B, area of the base was 60, times the height of the prism, which is 25. And now 25 times 60 is 1,500. And let's be careful with our units, centimeters cubed. So again, be careful with everything and making sure you're using the right variable in the right context. All right, find the volume of this prism. We're talking about a trapezoidal prism. And so volume is still area of the base times the height. And again, we got to keep, well, it's actually, let's go ahead and do our area formula for the trapezoid, which is 1/2 base 1 plus base 2 times height. Once again, we've got two H's here. Again, in context, we got to keep this straight. 1/2 base 1 of the trapezoid is going to be this bottom base here, the 4. Base 2 of the trapezoid is the top base, which is 2. And then height of the trapezoid is this one here, so that is 1.5. Let's see, 4 plus 2 is 6, times 1/2 is 3, 3 times 1/2 is 4.5. Just to make sure. Aha, I did it right. That's 4.5 centimeters squared. Now we jump over to the volume formula. Area of the base is 4.5 times the height of the prism, which is 6. Then 4.5 times 6 is 27 centimeters cubed. Most difficult thing here is keeping track of which height applies where. Context is everything. All right, here we have our first oblique prism. Volume is still area of the base times the height of the prism. So let's do our area formula. Looks like I've got a rectangle here on bottom, which is a parallelogram, so we're using base times height. So base of the rectangle is 10. Height of the rectangle is 15, because that's this direction here. 10 times 15 is 150 feet squared. Now let's jump over to the volume formula. Area of the base is 150 times the perpendicular height of the prism, which here is my 12. And 150 times 12, 1,800 feet cubed. So nothing too difficult so far. All right, volume formula for a cylinder. I should have put this up earlier, but it's okay if it's here. Again, same idea. If we think of it as the circular prism, area of the base, with the base being a circle, is just pi r squared. So if I put in a pi r squared there, I get this formula. So nothing special. We're going to round to the nearest tenth because pi makes that happen. So volume equals pi r squared h. So volume equals pi times the radius is 1.8 squared times the height is 1.8. Pi times 1.8. And it looks like that is just going to be cubed. 18.3 centimeters cubed. All right, example 5. Let me see, how many examples do I have on this? 6. Okay, an oblique cylinder. Again, exact same idea. Volume equals pi r squared h. As long as I have the perpendicular distance, I can use that, or the perpendicular height. So pi times radius is 15, squared times height is 25. Oops. Pi times 15 squared times 25. 17671.5. Oh, that's feet, not meters. Feet cubed. Now that I write in that, did I use cubed in the last one? Yeah, I did. Okay, last one. Now we got to do a little bit of calculating here because I am not given the radius or the height. I'm giving this slanted height here, but not the true height. So let's do radius first, okay? Looks like the diameter equals 8 inches. Therefore, the radius is going to equal 4 inches, just dividing by 2. Now I'm going to take advantage of this right triangle here, that if this right-hand side was 13, on these obliques, they slant in the exact same. Therefore, that is 13 inches. We now have a right triangle here that we can use Pythagorean theorem on, or you can understand or remember your Pythagorean triple, and you know that as a 5, 12, 13 right triangle. So that's going to be 12 inches. So then we're just going to plug in volume equals pi r squared h. pi times radius is 4 squared times 12. Pi times 4 squared times 12 is 603.2 inches cubed. So there you have it. Oh, whoa, I'm sorry, I forgot about example 7. I lied. And this is the most interesting one of the whole set. Okay. Prisms A and B have the same width and length, but different heights. So I can look at this and see that sure enough, yes, it's a 4 by X and a 4 by X. Different heights, we got 5 and 9. Okay, if the volume of prism B is 128 cubic inches greater than the volume of prism A. So I'm going to call this volume of A and volume of B. And it looks like volume B is 128 inches greater than the other, so that'll be volume A plus 128. What is the length of X? Well, let's see. Volume A is going to be area of the base times the height, which I know the volume area of the base here is just going to be 4 times X. So this is 4 times X times 5. Therefore, the volume of A is equal to 20X. All right, let's see what we can do for volume B. Volume B is going to equal 4 times X, because again, that's the area of the base there, times the height, which is 9. So the volume of the base, volume B is just 4 times 9 is 36X. Now I'm going to use my substitution property for systems of equations to substitute into this equation. Let me do that in a different color. To substitute into this equation. And what I'm going to do is replace volume A with 20X and volume B with 36X. So whenever I do that, I'm going to get volume B is 36X equals volume A is 20X plus 128. Now that gives me an equation that I can solve. Subtract 20X on both sides. Gives me 16X is equal to 128. Then we divide both sides by 16, and therefore X equals 8. So what is the length X of each prism? Well, sure enough, we've got X is 8. Now, on a problem like this where I did a lot of fooling around with it, I want to go ahead and double check that. Let's go ahead and calculate the volume of each prism. So I know that the left-hand one is just going to be 4 times X, which is 8, times 5, which gives me 160 inches cubed. The one on the right is 4 times 8 times 9, which is going to give me 188 inches cubed. And 288. 288 minus 160 is 128. So sure enough, the volume of prism B is 128 cubic inches greater than the volume of prism A. So to recap that, what we did was we started off by writing the volume formulas for each, we started off by writing that volume B is going to be 128 plus volume A. That came from the second equation. Then I calculated the volume of each one with the X in it. So here we had this and this, same idea, worked our way down to get 20X and 36X. Then I went and plugged in 36X for volume B, 20X for volume A, solved for X. Well, that's all I got for you today. I hope that wasn't too confusing. I know that was a lot of stuff, and we're right at 30 minutes now. I apologize for being so long, but like I said, you're not even going to use the surface area stuff. For now, the volume stuff will come up quite a bit when you get to calculus, so I wanted to cover that. Well, that's it. Take care. Stay patriotic.